All right, everybody. So in this video, we are going to go over some questions from acid-base chemistry. Let's start with, say, this question over here. Click on the hydrogen in the line structure of citric acid is likely to be the most acidic. Okay, and let me take a screenshot. So now the most acidic has to be one of these hydrogens. Okay, so these are the candidates. Okay, I would have included this, but the thing is, it does not, it is attached to oxygen, but compared to the other ones, it does not have the second feature, right? The second feature means we have the charge delocalization when we have the negative charge one bond away from the double bond. Okay, because you don't have that, it's going to be one of these, let me call this A, B, and C protons, and not this because of the second feature. Okay, let me call this D. D is out. Okay, and then between A, B, and C, A and C have the same situation. Okay, so you have the second feature and also electron withdrawing groups approximately at the same distance from the anion bearing side. Okay, so but when it comes to option B over here, you can see that this the charge bearing side would be this spot over here. Okay, and this is going to be just one bond away from this OH group, which is going to be an electron withdrawing group. Okay, and as a result of that, the proton B can be expected to be more acidic than the other ones. It should be the most acidic proton because it is closest to an electron withdrawing group. Okay, so the correct answer must be that particular proton. So let's go back to the side and check. Okay, the correct answer is this particular proton over here. All right, second question. The pH of common lemon flavored sodas is close to 3. Okay, and then let me see, we can do two questions here at the same time. Okay, you are given the pH. Okay, so this is your pH. The pH is 3, meaning H3O plus concentration is 10 to the power of minus pH, which is 10 to the power of minus 3. And then we know for a weak acid, this value, okay, the H3O plus concentration should be equal to the initial concentration of the acid times Ka, the square root of the entire thing. Okay, therefore C naught times Ka must be H3O plus concentration squared, and therefore they're asking for the molar concentration of citric acid, that means C naught. Therefore C naught must be equal to H3O plus concentration squared divided by Ka. Okay, and then in this case you're given all the values. I believe H3O plus concentration is given to you, that is 10 to the power of minus 3 squared. Okay, which we calculated over here, and divide this by the Ka of citric acid, which is let me see if I can find it really quickly. All right, that's going to be 7.4 times 10 to the power of minus 4. Okay, so 7.4 times 10 to the power of minus 4. So if you do this calculation, then you're going to get 10 to the power of minus 6 divided by 7.4 times 10 to the power of minus 4. So this should be 10 to the power of minus 2 divided by 7.4. Right. And if you do this, if you plug and chuck these numbers onto your calculator, then you are going to get, let me see, to the power of minus 2 divided by 7.4. 7.4 is, this is equal to 0.0135. 0.0135, and that should be your answer. 0.00 actually 0.00135. Okay, now let's go back and enter that answer. Okay, so let's see, 0.00135. The correct answer is yeah, it's in between whatever the value top hat has here now. Okay, now moving on to the next question. The mass estimate the grams of citric acid added to 355 milliliters soda can. Do not include units and avoid using scientific notation. Okay, that's fine. So, okay, so you know the concentration 0.00135, and then you are given the volume. You just need to find the mass in grams. Okay, now let's do this. So we know the concentration is equal to number of moles over volume. Okay, and then therefore number of let me see, yeah, the number of moles is equal to concentration times V. So the concentration is let's say 1.35 times 1, 2, 3 to the power of minus 3 molar, which is this number over here, the number we got before from the previous calculation. And then this is gonna be moles over liters, and multiply this by the volume, which is 0.355 liters. So liters cancel out, you're gonna get the answer in moles. Okay, and if you do that, you are going to get, let me see, 0.355. Okay, and if you do that, you're gonna get 4.8 times 10 to the power of 1, 2, 3, 4. Okay, minus 4 moles. Okay, and then we know the molar mass, or the number of moles, is equal to mass divided by the molar mass. Okay, therefore mass is equal to number of moles times the molar mass of citric acid. And we need to find the citric acid molar mass in a second. Okay, and then what we need to do is we need to multiply 4.8 times 10 to the power of minus 4 moles by the molar mass of citric acid, which is 192 point, let me see, okay, 192.1, right? 192.1 grams per mole. Moles cancel out, you're going to get the answer in grams. So let's try that. 192.1, 192.1. Okay, you're gonna get 0.092. Okay, so therefore the mass must be 0.0921 grams. Okay, now let's go back. 0.0921 is our calculated number. Okay, and if you go to that question and then ask to show you the value, and 0.0921 is within this range, which is great. Okay, now moving on to next question. The pH, estimate the pH of lemon juice. You're given the concentration in grams per liter. Okay, so this is a different initial concentration. So let me see. Okay, so we need to pay attention to 48 and then 7.4 times 10 to the power of minus 4. Okay. All right, let's try this question. Okay, so Ka is 7.4 times 10 to the power of minus 4. For citric acid, I just want to have that value handy. We know for a weak acid, the H3O plus concentration is initial concentration times Ka square root. And then the C naught is this value over here. But the thing is, this is in grams per liters. So you need to convert this to moles per liters. So to do that, okay, so we have 48 grams, okay, per liter. If you divide this by the molar mass, which is 192.1 grams per mole, okay, you're gonna get the answer in 48 divided by 192.1 in moles per liter. Okay, and that value happens to be 48 divided by 192.1, which is 2.25. Nice. 0.25 moles per liter. Okay, so we just plug and chug these numbers now. So we have 0.25 and then multiply this by the Ka, which is 7.4 times 10 to the power of minus 4, and use the square root of that. And if we do that, okay, multiply by 7.4 times 10 to the power of minus 4. And then we need the square root of the entire thing. Let's see. Okay, I'm going to try this one more time. So the square root of 0.25 multiplied by 7.4 times 10 to the power of minus 4 is 0.0136. Okay, it's going to be 0.0136. Now they're asking for the pH. Okay, pH is the minus log of H3O plus concentration, is 0.0136. That minus log of that is 1.86. 1.87. Okay, so let's try that value. Oh no, it doesn't give us a value. Anyway, so that's how we tackle this problem. So we have the C naught, we have the Ka. Okay, you just multiply those two numbers and then get the square root of that. That will give you the H3O plus concentration, and then you take the minus log of that value to get the pH, which is great. Okay, now with that, let me see if we have some of the questions. Yeah, we have a few. Approximately how many times stronger is phosphoric acid than citric acid? Okay, so the question is, it's about the Ka. The strength of an acid depends on the K, okay, the Ka value. Okay. So acid strength is directly proportional to the Ka value, and therefore what we can do is, so we have phosphoric acid, which is stronger. So Ka of H3PO4 divided by the Ka of citric acid should be 7.1 times 10 to the power of minus 3 divided by 7.4 times 10 to the power of minus 4. So that's gonna come out to be, let's try this, okay, 7.1 times 10 to the power of minus 3 divided by 7.4 times 10 to the power of minus 4 is about 10 times 9.59. This is 9.59. I would say about 10. Okay, so the answer must be around 10. Let's try that. Okay, so the correct answer is yeah, it's around 10, which is great. And then the next question: which of the following factors is mostly responsible for the increased acid strength of phosphoric acid versus citric acid? Okay, here's phosphoric acid. You can see that our electron withdrawing groups are much closer to each other. On the other hand, in citric acid, the electron withdrawing groups are not as close to the charge bearing or the conjugate base site. Okay, therefore I would say it's about the neighboring group effect or the inductive effect. So the correct answer is inductive effect. Okay. Okay, click on the most acidic proton and the most basic center in the molecule of aspartame, this whatever this molecule is. Okay, so when it comes to, let me take a picture actually quickly. Okay, so acidic protons, so we have hydrogen bound to nitrogen and hydrogen bound to carbon and hydrogen bound to oxygen. So based on feature 1, which is the charge bearing atom, the molar negative atom is going to be more stable when it is carrying the negative charge, right? Therefore, it's going to be between, no, it's going to be just this. It's going to be just this proton, which is going to be more acidic because based on feature 1, because that's the only one that will generate the negative charge on oxygen atom compared to nitrogen or carbon on the other cases. And then on the other hand, when it comes to the, so this is the most acidic. When it comes to the bases, then again, the basic centers are the opposite. Okay, so if we have the least stable conjugate base, they are going to be more basic or more reactive. Okay, and then that has to be a lone pairs on nitrogen in this case, because you don't have lone pairs on carbon. You have lone pairs on oxygen, but oxygen is more electronegative than nitrogen. Therefore, they're going to hold on more tightly to those lone pairs without making them reactive. Okay, so when it comes to nitrogen, we have 2 of them. So here's 1. Okay, here's 2. And between these 2, now we go to the feature 2. So when it comes to, let's call this A and B. Okay, and when it comes to something like say B, you have a double bond, 1 bond away from a lone pair. So this double bond. Okay, what's going to happen is this can participate in charge delocalization or resonance stabilization. Okay, and as a result of that, the basicity of side B is going to be decreased. And on the other hand, for A, you don't have a double bond, 1 bond away from this lone pair. Therefore, I would say option A is going to be more basic than option B. Okay, because we always go with feature 1 first, then feature 2, then feature 3, and then for basis we also talk about primary, secondary, and tertiary. I mean, how secondary amines are more basic than the primary and tertiary. Okay, so let's see if Top Hat agrees with us. There you go. Yep, Top Hat agrees with us. which is great. And next question, determine the ratio of base to acid concentration needed to maintain a pH at 3 using citric acid citrate buffer. Okay, so this is again coming down to let's say the Henderson-Hasselbalch equation. So what we need is pH 3, and then we have the pKa of that, right? Okay, so let's move to that question. Okay, let's try it. Anyway, so the Henderson-Hasselbalch equation is, okay, pH is equal to pKa plus log A minus concentration over HA concentration. Now the question is asking for this ratio. Therefore, log A minus concentration over HA concentration is equal to pH minus pKa. Therefore, A minus concentration over HA concentration is 10 to the power of pH minus pKa. Okay, this is what we need. So we are given the pH, it's over here, and then the pKa for citric acid is minus log 7.4 times 10 to the power of minus 4, which is gonna be, let me see, the minus log 7.4 times 10 to the power of minus 4 is 3.13. 3.13. Okay. So therefore, this should be pH is 3 minus 3.13. You're going to get 10 to the power of minus 0.13. Okay. And then what this means is A minus over HA is 1 over 10 to the power of 0.13. Okay, so what is that? For every 1 A minus, we have 10 to the power of 0.13 of HA. Okay, so 1 over 10 to the power of 0.13 is 0.74. Okay, so and then again, this makes sense because pH is less than the pKa, therefore the acid form is dominant, therefore you should have more of the weak acid. Okay, and that's what this says. Okay, so this is again 74 over 100. Okay, so you have more of the weak acid. That's what this means. Okay, 0.74 must be your answer for that question. Moving on, arrange these carboxylic acids in order of increasing acid strength. Okay, you are given some carboxylic acids, and then let's see what's going to happen here. So, okay, no, I should take a screenshot and then work on that again. So now, when it comes to all of these, we have the hydrogen bound to one of these oxygens, right? So that means, I mean, the feature 1 doesn't help us in any of that. And then when it comes to feature 2, all of them have double bond, one bond away from the negative charge. Okay, and then after that, there's going to be resonance stabilization or charge delocalization. Therefore, feature 2 doesn't cut it. And when it comes to feature 3, the inductive effect or the neighboring group effect. Okay, so we have for lactic acid, we have an electron withdrawing group, which is going to stabilize the negative charge once it is formed here. And then when it comes to succinic acid, this electron withdrawing group is far away, I would say. okay, but it's still there. Okay, but when it comes to the tartaric acid, we have an electron withdrawing group, one bond away from here, and then you go down another bond, we have another electron withdrawing group, and there's another one. So I would say tartaric acid is going to be the most acidic, okay, because it's going to be stabilized by many electron withdrawing groups, and then lactic acid, and then succinic acid. Yeah, let's see. We can check the answer actually. Yeah, there you go. That's the correct answer because of the electron withdrawing group of the inductive effect. Okay, so I think we are almost done here. Basic additives. Let's do a few other questions. Okay, so we covered all the basic stuff, I mean acidic stuff at least. The chemical compounds such as calcium carbonate and calcium oxide are used as acidity regulators too. Calcium carbonate undergoes this chemical reaction in acidic medium. Okay, so here's this. And then what should happen to the pH of a solution in which this reaction takes place? Okay, so now if this reaction takes place, then the calcium carbonate is consuming H3O plus. Okay, so that's going to consume H3O plus. That means it's going to decrease H3O plus concentration. Therefore, pH has to increase. Okay, so the correct answer must be increase. Okay, equilibrium perturbations. Which of the following graphs represents the change back to equilibrium when water evaporates from food products in which this reaction takes place? Okay, now water evaporates. When water evaporates, all the aqueous species concentrations should increase. Okay, but you can see that we have more aqueous species on the reactant side. H3O plus is 2. That's a coefficient in front of H3O plus, which is 2. But on the product side, the only aqueous species is calcium 2 plus. That's just one of them. Okay, so therefore I would say the reactants are going to be affected more, meaning the reactant concentration is going to increase more than the product concentration. Okay, if that is the case, the Q is going to become less than the K. Okay, so it has to be between 1 and 4, and then because the all right, so it's going to be between 1 and 4 because we are going to increase the reactant concentrations more than the product concentrations. And then what is going to happen to the pH? Okay, so because of the operation, all the concentrations go up, including the H3O plus concentration. Okay, so the increase of the H3O plus concentration due to perturbation is much greater than what is gonna be neutralized by the shift of the equilibrium. Therefore, H3O plus concentration should overall increase, meaning pH should go down. So the correct answer must be option 4. Oh, there you go. Okay. All right, let's do one other thing. Okay, one last question. So equilibrium perturbations, which of the following statements describes the changes that will take place if the total external pressure on the system is increased? Okay, so when you increase the pressure, that means it's going to be equivalent to increasing the concentration of gaseous species. So you are increasing, so only gaseous species in this reaction is carbon dioxide gas, right? So if you increase the pressure, you are increasing basically the concentration of carbon dioxide, and then that will increase the product concentration. And let's say we're talking about the rate, right? So if the product concentration if increased, then the rate backward should be greater than the rate forward. Okay, so here are the options. The rate backward will increase compared to the rate forward. That is correct. Okay, so rate backward will increase. So it has to be between options A and D. Only difference is in one case pH will increase, the other case the pH will decrease. So let's think about the pH here. Now if that is the case, if you're increasing the reverse reaction rate or backward reaction rate, that means it's going to produce more H3O plus, more reactants. Okay, the shift is going to produce more reactants. Therefore, H3O plus concentration go up. Therefore, the pH should go down. So the correct answer is option D. Yeah, it's up to you. Option C. Yeah, because this is the option D says the backward reaction will decrease. So we already established that backward reaction will increase. Therefore, the correct answer is option C, not D. That's correct. Okay, so we had to read carefully actually. So we already established that the backward reaction is going to increase more. Then the D says the backward reaction will decrease. So it cannot be the answer. It should be between A and C. And then the pH has to decrease because it's going to produce more H3O plus, meaning H3O plus concentration is going to go up. Okay, now anyway, moving on to the next question, the temperature effects. If the two reactions are exothermic, if these two reactions are exothermic, here you go. Which of these following statements is true? Exothermic means, okay, the products are going to have a lower potential energy than the reactants. Okay, so therefore, increasing the temperature. In all cases, we are increasing temperature. Increasing temperature should favor the formation of the reactants because reactants have a higher potential energy. Okay, and the higher temperatures favor the state with high potential energy. So with that in mind, let's look at the answers. Okay, increasing the temperature would reduce the impact of adding calcium oxide on increasing the pH of the system. Okay, increasing the temperature would reduce the impact of adding calcium oxide on increasing the pH of the system. So if you increase the temperature, that's going to favor the reactant formation. Therefore, the impact of adding calcium oxide should be reduced. Okay, so reduce impact, that is correct because we are adding calcium oxide to generate calcium hydroxide to neutralize some acids. Okay, and then but increasing temperature is going to favor the not formation of calcium hydroxide. Okay, and that's going to reduce the impact of adding calcium oxide then. Okay, the reason why we add calcium oxide. And then that is correct, I think. And then increasing the temperature would reduce the impact of adding calcium oxide on decreasing the pH of the system. So calcium oxide, adding calcium oxide is not decreasing the pH. It's going to increase the pH because calcium oxide addition produce calcium hydroxide, right? So which is going to be a base. So now therefore this statement is incorrect because calcium oxide is not decreasing the pH, it is increasing the pH. So that is, statement B is incorrect. And let's think about the next one. Increasing the temperature would not affect the impact of adding calcium oxide on increasing the pH. No, I wouldn't agree with that. Okay, so it certainly affects this reaction because both reactions, okay, it's going to favor the reactants more than the products. Okay, therefore that is not a correct statement. And then the same thing here. So C and D are incorrect as well. So the correct answer is option A. Okay, so one last question. reaction directionality. Consider the acid-base reaction between a generic carboxylic acid and ammonia. Are these reactions likely to be product favored or reactant favored? Okay, consider the base reaction between generic carboxylic acid and ammonia. Okay, now the idea is, I think I should take a screenshot of this. Okay, now you have the pK, right? Let me write this down. What we have here is RCOOH, okay, with reacting with NH3 to produce, let's say, RCOO minus plus NH4 plus. Okay, so RCOOH is the weak acid, and that has a pKa of 4. Okay, therefore Ka must be 10 to the power of minus 4, and ammonia has a pKb of 4.7. Therefore Kb must be 10 to the power of minus 4.7. On the other hand, we can do, I can rewrite this actually just to make things clear. Okay, this. So the pKa or the Ka, that's right. Okay, the K, no, it's not going to show us. I'm going to use the color green maybe. Okay, so for carboxylic acid, the Ka must be 10 to the power of minus 4 because pKa is 4. Therefore, Ka is 10 to the power of minus pKa, which is that. And for ammonia, the Kb is 10 to the power of minus 4.7 because pKb is 4.7. Kb must be minus 4.7. And then for the conjugate base of the acid should have a pKb of 14 minus 4, which is going to be 10. Okay, so the Kb for RCOO minus should be 10 to the power of minus 10. And then for NH4 plus, the conjugate acid of ammonia must have a Ka value of, or pKa value of 14 minus 4.7, which is 9.3, therefore 10 to the power of minus 9.3. Okay, you can see that we have smaller Ka and Kb values on the product side, meaning these are less reactive. Okay, that means that they are more stable. So our products are more stable compared to the reactants because the Ka and Kb values are smaller. As a result of that, we can expect this reaction to be product favored. Okay, so that should be our answer. Let's try that. It should be product favored. Okay, because Ka and Kb values are smaller on the product side. Okay, so that covers all the questions from this particular assignment. I hope this helped. I'll see you guys in class. Bye, everybody.